of our event. 3 talks, and the first is by Thomas Stocker from the University of Bern, who will talk about climate change from knowledge to action. Thomas.
Thank you very much, John. Good morning, everybody, and should like to first say thanks to IAMAS to have me here in Montreal, a city, in fact, that is very close to my heart because just about 30 years ago, I came to Mcgill University to the Department of Meteorology, to Lawrence Mysak. He's over there in the audience, and started my first postdoctoral assignment. So Montreal is a very special place. Now that was 30 years ago, and in these 30 years many things happened, and certainly things happened that are the basis of what I will be talking about today. In this short 30 minutes that I've been given, I wanted to say a few things about climate change, how the scientific community has prepared the path from knowledge to action. And I want to start with this photograph that you all know. It's the Earthrise, but not the first Earthrise from Apollo 8 mission, but the one from Apollo 11 mission, where if you inspect these photographs, you already see some technological development. The Earth here appears in a much sharper view in Apollo 11. But I took this photograph for 2 reasons. The first reason is that it's now 50 years, almost 50 years since man landed on the moon. And that moon landing is also a special event for the University of Bern, in particular the Physics Institute, which is my home. Our colleagues in space physics, they landed the first experiment on the moon, the solar sail that captured the solar wind and the particles from the solar wind. A very simple physical experiment that was carried out on the lunar surface, erected there even before the American flag was erected. The second reason why I show this picture is because you see in this one image 2 very different spaces, 2 very different locations, one a habitable location and practically in the immediate vicinity an inhabitable location, the moon's surface. And of course, we all know what the ingredients of habitability are. It's water, but it's the atmosphere. And the atmosphere is the topic, the scientific topic of IAMAS for the last 100 years and hopefully for the next 100 years as well. So what we learn about the atmosphere, its physical processes and its functioning as one component of the Earth system is absolutely fundamental to understanding habitability and also to manage habitability on this planet. If we don't know it, we can't manage it, as was already said this morning. I want to touch on 3 points, really. I want to look back very quickly on 40 years of climate assessment as the basis how to transport complex scientific knowledge to a broader public and in particular to decision makers. There are a few milestones that need to be remembered that bring us right up to the Paris Agreement of 2015. Then out of 2 scientific topics that appear to me rather exciting, I want to highlight tipping points, and I share with you a few thoughts that I want to make, that I think there is today somewhat in the broader public a confusion about tipping points, and I think it's our responsibility as scientists to really provide the robust knowledge that allow us to move forward and to take decisions regarding climate change. Geoengineering is another one, an emerging topic that I think personally it is one of these things that may potentially constitute dangerous interference, not just the emission of carbon dioxide and other greenhouse gases into the atmosphere, but also actions as such are dangerous interference. And last point, a few considerations on the 100 years and the next 100 years. Let's now move back to 1978. You will see in a second why 1978. And just reflect for a while how scientists were looking at this chart and what that chart, which you are all very familiar with, told the scientists in 1978. You see a few annual cycles of the atmospheric concentration of carbon dioxide, extremely high precision measurements by David Keeling at the time. You see an increasing trend, and there were only a few scientists who knew what the origin of that increase was. And they had it quite right, as I will show you in the next slide. Among these colleagues were two friends of the University of Bern, of my institute, Uli Siegenthaler and Hans Oeschger, who in 1978 published a paper in Science magazine entitled Predicting Future Atmospheric Carbon Dioxide Levels. And that paper, in that paper, they presented a very simple box model of the carbon cycle, consisting of a box for the atmosphere, a box for the biosphere, and a box with two compartments for the global ocean. And with that simple model, with the inventories and the fluxes and the timescales that they use for the exchanges, they were able to make some global statements about the carbon cycle. Towards the end of that paper, there is a remarkable sentence, and I quote here, "A maximum permissible atmospheric CO2 level might be found, which should not be exceeded if the atmospheric radiation balance is not to be disturbed in a dangerous way." This was 1978, and if you see the word dangerous, everybody comes to mind the UNFCCC Article 2, that dangerous anthropogenic interference is to be avoided. These colleagues already in 1978, being aware of that very short, relatively short period of carbon dioxide measurements from the atmosphere, were able to essentially point the finger to the right problems and understand in a quantitative way our Earth system. And to demonstrate that, I show you what their prediction was in that paper as well. 1978, Siegenthaler and Oeschger predicted a carbon dioxide concentration of 363 ppm for the year 2000. And now I uncover what has been realized. And you see their prediction was pretty spot on, only about 1.6% away from what was realized then in the year 2000. And how that continued, we are all aware. Obviously, that increase needs to be put into a larger context, and here I show one of the curves we are proud of at the University of Bern with the help of many colleagues, in particular a European project for ice coring in Antarctica, Ipcc, that allowed us to reconstruct the last 800,000 years of carbon dioxide concentration in the atmosphere. You see here natural fluctuations without the interference of man. I highlighted at the right end the concentration at the year IAMAS was founded. 1919, the concentration of carbon dioxide in the atmosphere was 303 ppm, and that you see at the right end. And it's actually about the same value as the highest value that we measure over the last 800,000 years, a value that was assumed at the interglacial around 330,000 years before present. In the meantime, 2019, we are at 415 ppm, an unprecedented increase whose origin, as I said, was already understood and quantitatively reported by scientists in the 1950s for the first time, and then very impressively in the 1970s. Knowledge that was around in the scientific community, but a long way from action. There were other individuals. This is Wally Broker, who unfortunately passed away earlier this year. I had the privilege to have a postdoctoral stay of 2.5 years with him in the mid-90s. And in 1995, he wrote this paper in Science, Climatic Change, Are We on the Brink of a Pronounced Global Warming? And if you read the abstract, you see there already one of the important points that still today quantitatively is an important question. The balance between the dust load or the aerosol load that man puts into the atmosphere and the greenhouse gases that produce the warming. And he said if the dust load will decrease in the future, then in a few years, from the perspective of 1975, we will see a pronounced global warming. And Wally was right. 4 years later, there was a small committee, a very small committee, that produced the first climate change assessment. And you see that already in the title. Climate appears in the title, scientific assessment. These pioneers, under the leadership of Jules Charny in 1979, produced this important paper that you can read. It's available as a PDF on the internet. They call it very modestly an ad hoc study. But the important ingredients of such an ad hoc study or a scientific assessment are already in there. They talk about consensus. Consensus, a very important element for later, more formally organized assessments, such as those by the Intergovernmental Panel on Climate Change. In their 1979 assessment, they say the consensus of these studies has been that increasing carbon dioxide will lead to a warmer Earth with a different distribution of climatic regimes. And I purposely quote that sentence because they already pointed to the fact that the impacts are felt on a regional basis and in climatic regimes which are influencing the regions and local areas and therefore people. What we then realize is that in the mid-80s to the late 80s, a few pioneers have convinced the more formal bodies that existed in the meantime, like the World Meteorological Organization and the United Nations Environment Program, to bring to life the Intergovernmental Panel on Climate Change, the Ipcc, in 1988. That was an effort in preparation of the first Earth Summit in 1992, and in good time, that is in 1990, the first assessment report was available. And I still remember when I was a postdoc at Mcgill here, there was a visitor in 1989, towards the end of 1989, Francis Bretherton, who was one of the lead authors of one chapter, and he came by, and as a postdoc I was given like half an hour to talk with this prominent scientist, and he already then admitted that this is a huge burden to write this assessment chapter with hundreds of references, and he didn't know how to keep the time plan and the pressure, etc., etc. But they succeeded. They presented that really legendary first IPCC assessment report, which was the basis ultimately for the UN Framework Convention on Climate Change. This is history. 4 more reports have been published, and the 6th is now in the oven. It will be published. There were already a few special reports that are in the pipeline or have been published, the 1.5 report, but the sixth comprehensive report is expected to be issued in 2021. So what is in this 2013 report? I just want to recall four key statements. For the first time in Ipcc Summary for Policymakers, we included very simple language. This is a response to the criticism that the scientists tend to write long sentences with a lot of technical jargon, with a lot of numbers and uncertainties and ifs and nots and high confidence, low confidence and whatnot, and that this is difficult to absorb by the public and by decision makers. So we purposely strived for simple language, but language that, because it is embedded in the Summary for Policymakers, is actually approved by all countries in consensus. One of these statements was, warming of the climate system is unequivocal. Special thing about these statements are 2 points. The first one is that this statement exactly was already published in the SPM of the fourth assessment report in 2007. A second point was that in 2013, if you remember, we were in the so-called non-existent climate pause, in the pause of global warming that was really hyped by the media. And also governments, of course, had taken note of that. And so we were really challenged as a group concerned with the Summary for Policymakers how to counter that public atmosphere of, oh, maybe global warming is no longer happening, because if you look at this very short period from 1998 to 2013, it appears that that trend there, which everybody knows should not be taken as climatic, is a trend that is 3 times lower than the 50-year trend of the global mean temperature anomaly. So having that statement in there was important to repeat it and to really firmly embed it in the Summary for Policymakers. This one is a statement that I'm personally very proud of, that we could have that passed by all the governments. Human influence on the climate system is clear. It's essentially a nutshell summary of the entire detection and attribution science, which since the third assessment report really has developed in a tremendous way. That the science that combines high-resolution observations with the best models available to make an attribution statement how much of the warming is actually caused by which radiative driver, be it greenhouse gases or aerosols providing some amount of cooling. Many people have bet against us that they said, well, you will lose that sentence in a blink of an eye, because there will be 2 or 3 countries that raise their flags and say, oh, well, you can't say that. Here is an alternative proposal, and consensus is a mechanism that gives a lot of power to an individual country who would object to a statement. But that statement has remained in the Summary for Policymakers because the underlying science was extremely robust and was relying on multiple lines of independent evidence. And that is certainly a message for all of us scientists who provide the knowledge for the next and future assessments. The robust knowledge will convince even the sternest skeptics. Continued emissions of greenhouse gases will cause further warming. That's a clear statement for action if you want to limit the warming. And to make that absolutely clear, we had this sentence in there: limiting climate change would require substantial and sustained reductions of greenhouse gas emissions. That statement you could interpret as the summary of the scientific basis for the Paris Agreement. The quantitative statement for that is here embedded in this figure. This was a figure that was very hard to pass. We negotiated and provided scientific arguments for more than 36 hours until the last country actually also agreed to the statement that this is an important figure and needs to be kept in the summary for policymakers. This is a figure that shows, independent of the individual scenarios, the near linear relationship between the cumulative total anthropogenic CO2 emissions and the warming, the global mean temperature anomaly relative to pre-industrial that is expected in the 21st century. It's a very powerful figure because it directly talks to climate targets, and that you can look at if you look at the 2-degree warming that then informs you through this curve and this relationship, including its uncertainties indicated in these cloudy areas, the amount of carbon in total that can be emitted to be consistent with this target. 790 billion tons of carbon, give or take. Of course, very large uncertainties on the order of 20% still today, but it gives you an indication where we stand relative to a politically declared target. And today, we just have to admit that over 3/4 of that carbon budget has been exhausted, and we are on the way to basically exhaust that entire 2-degree target. And for the 1.5-degree target, the situation is even more difficult. But I want to now make a direct connection here to the Paris Agreement and that passing on December 2015. I think the science has played an extremely important part in that, and with that, I just acknowledge the individual contributions of everybody, in particular those who are working in atmospheric science, in any aspect of atmospheric science, and this is a big thank you to everybody. Perhaps a bit late, but I think entirely appropriate at a centenary. In that agreement, of course, we know that the goal is clearly set, holding the increase in the global average temperature to well below 2 degrees above pre-industrial, and to reduce rapidly global CO2 emissions and reach net zero in the second half of the century. That, again, that statement, a direct consequence of the carbon budget. So the first conclusion that we can draw is without basic science, there is no scientific assessment. The basic science is absolutely essential. Otherwise, your assessment will be actually torn apart in the air if you present it. Scientific assessments of the Ipcc are the foundation of the Framework Convention. That was the first one, and the fifth one, with all the predecessors, formed the scientific basis of the Paris Agreement. And I need to say now, with a distance to that process in which I was deeply involved, the pace of assessments and political and public expectations have really increased considerably. And that is a burden to the scientists, and we have to recognize that, and our funders have to recognize that as well. Let me now come to the second point here. Tipping points is certainly something, when you talk about climate change, it's one of the big questions that the public has. Where do we stand? Which parts of the climate system can become dangerous players in the near future? And here I basically sense a confusion in the public, and it's the scientists' responsibility to establish firm knowledge. I'll just give you two examples. One is the meridional overturning circulation in the North Atlantic. You see here various measurements that have started in 2004. It's the rapid array that allows us to observe various components of the circulation that provide a measure for the AMOC. The AMOC itself is the second curve from the top. And you see there, if you analyze those data over the last 15 years or so, you see there are different conclusions. If you look to a short time, you see a decrease in this AMOC, but then if you look at the second half, you may actually find an increase, or is it perhaps this one, a slight decrease? We don't really know. We can't really say at this point, because the observations are too short. So either we need to complement these observations, these oceanographic observations, with other fingerprints that allow us to draw a conclusion, or we have to observe more precisely and longer. But there are also the models that may actually shed some light here. This is a simulation using the NCAR model that goes out to the year 2500. You see here the increase of temperature in 4 scenarios, one very extreme, a business as usual scenario, and the corresponding response of the AMOC, where you observe a bifurcation, a feature that is a part of that nonlinear system of the atmosphere, ocean circulation in the North Atlantic. That would be a true tipping point if that bifurcation were to occur. Another one, of course, is the fate of the ice sheets. For example, with the satellite measurements from GRACE, we can basically weigh the Greenland ice sheet on a monthly basis. You see this ice sheet is on a terrible diet. It's not recovering after a winter. The summer is always taking a heavier toll on the mass of the ice sheet. We're losing 400 gigatons per year. Antarctica is not faring better. We're losing there at the moment 130 gigatons of ice a year, and the sum of that amounts to about 1.3 millimeters per year of sea level rise. If you go further in time, in the Anthropocene, that is the next 10,000 years, we are talking about possibilities if the temperatures are not checked and if the Paris Agreement will not basically unfold its effects. And Antarctica and Greenland could actually enter into states that have considerably less ice than what we have today. These, of course, are dramatic scenarios. Let's hope that these scenarios will not materialize. So the understanding of tipping points in the Earth system is rapidly growing, we may say that, but the observational capability is still limited, and yet it is crucial to make progress. Because of this high policy relevance, there is a confusion of messages. The media bring other messages than the messages that are around in the scientific communities. And even within the scientific community, it occurs to me, sometimes we hear conflicting messages ranging from drama to basically, well, maybe it's not so bad, we don't really know. So I think time has come where we need to stand back and reflect, and a usually good way to reflect is actually to carry out an assessment, bring people together at one table, and try to seek a consensus, a scientific driven consensus that allows us to make statements with confidence levels and with uncertainties. So let's now come to the third and last point of substance. I want to say a few words about an emerging topic that is in the heads of many and is also increasingly in the heads of decision makers, and that puts the scientific community into a particularly important point of responsibility, and that responsibility we cannot avoid. Now, geoengineering, there are many ideas around. In the last IPCC report, we published this figure, which summarizes a dozen different ideas, 6 of which are in the carbon dioxide removal part. That's one technology or one methodology, and the other one is the solar radiation management, on which I want to focus now. There are some very recent simulations that are scientifically extremely interesting and fascinating. For example, injecting sulfur dioxide into the stratosphere at different locations with different temporal evolutions, so as to basically manage the temperature evolution not only of the global mean temperature, but of also interesting and dynamically relevant derived quantity of temperature. In that particular experiment, two further quantities of temperatures are being managed. That is the interhemispheric temperature gradient and the equator to pole temperature gradient. And you see here in the pictures on the right-hand side that with this intervention, it's actually possible to keep the global mean warming, but also these more dynamically relevant quantities of temperature gradients within very tight limits of today. Now, this seemingly is a success if you focus your view only on temperature. What that does is it provides you with a huge commitment to deposit lots of aerosols, of sulfate aerosols, into the lower stratosphere. You see the simulated distribution here towards the end of the century. So basically, to counteract the pollution of carbon dioxide in the atmosphere, we add another element of pollution into the atmosphere at a particular region within the atmosphere, and that is the lower stratosphere. What that does is it also modifies the temperature in the lower stratosphere. You see here a pronounced warming, and I wonder, I'm not an expert on that, but I do wonder what influence and what consequences such a change of temperature and therefore the available energy it has on chemical reactions in that very sensitive area of the atmosphere. It provides a commitment. Things appear to be linear if you ask the question, how much sulfur do we actually need to put into the atmosphere? But it's a humongous amount of aerosols. It's 10 million tons of sulfate per every degree Celsius that you want to cool and per every year. So a deployment of once that amount is not enough. You have to do it essentially every year. So it's a commitment, and that commitment has another consequence, which I think cannot be communicated often enough, and that is the so-called termination problem, as you basically bring the atmosphere into increasing imbalance with the greenhouse gas concentrations in the atmosphere. You're running and increasing the risk of abrupt climate change, which here happens in this simulation at year 50, when humankind decides to stop the deployment of sulfur dioxide into the atmosphere, and a very rapid relaxation of the global mean temperature happens at that time, with questions of adaptability of ecosystems and nature as a whole. The same thing happens for precipitation. You see two things at this right diagram. Precipitation decreases during your geoengineering experiment, so this is an unintended side effect. You don't really want to decrease precipitation worldwide, but once you stop, that also has a termination problem with a rapid increase of precipitation on a decadal timescale. That is, again, a question of adaptation. Let me come to the conclusion here. Geoengineering, in particular solar radiation management, bears risks that are global, unknown, and unquantified. Stratospheric resolving physical chemical models are required. It's my firm conviction we don't stop science, but we want to know more. We want to know the numbers. We want to have the quantitative information, how dangerous that actually is. That's perhaps a personal statement here. Geoengineering constitutes dangerous atmospheric interference with the climate system, and I here purposely quote or use similar language as in Article 2 of the Framework Convention, and threatens Earth stewardship. Let me now come to the last two slides, I believe. Basic atmospheric science, and that is what IAMAS is doing, is more than ever essential to understand the changing Earth and take informed decisions. So our work is not done. Our work is more important than ever. Assessments are ongoing. New assessments may be on the horizon, and your expertise is certainly known. Tipping points is something that the public is confused and sometimes scared of, and that requires objective and dependable scientific information. The IAMAS community is a key contributor to such an endeavor. This I've said already. It is my personal conviction, but that does not mean that one must stop or put a ban on the science, but rather to carry out the science in a responsible manner. And here comes to mind that in other areas of huge social responsibility, be it nuclear physics, be it gene technology, or KI, artificial intelligence. Also here, I think the scientific community has a special responsibility. I therefore propose to you that IAMS should develop and communicate a position on atmosphere-based climate intervention schemes and technology. And with that, I'm already at the end, and I thank you very much for your attention. I wish this entire vibrant community another vibrant 100 years. Thank you very much.
Thomas, that was really very interesting talk, thought-provoking. Time for one quick question, perhaps? If any, one from over there, from Jim.
Yeah, thank you. Thank you so much. I completely agree with your presentation. Jim Fleming, I was on the National Academy study on, we called it climate intervention. And we changed the name from geoengineering because Marcia McNutt, and she agreed that engineering was too precise of a term. We also moved solar radiation management into albedo modification. And so my question is on this NETS, this big challenge to store and reduce carbon dioxide, where are we going to store it, and isn't there a role in the future now for social scientists, for what can go wrong kind of people, when you want to modify the whole coastline or you want to change the whole world's mining engineering to erode rocks quicker? That just begs for sort of social science, historical, humanistic analysis. And could the new union with the two branches coming forward address that kind of issue?
I think you raise a very important point. It's no longer only the question about numbers that we provide in our community and that we still need to provide. For example, it's not known what is the storage capacity in different regions where the emissions actually occur and where these emissions then need to be stored, but also combine that with a more ethical, a more social science-oriented debate and discussion, a conversation with the entire community to actually ask questions about intergenerational justice and things like that. That is extremely important, and I do hope that that community actually, which to me still seems somewhat not tight, but perhaps with one leg still in the ivory tower, to come out of that tower. Our community has come out of that tower essentially 40 years ago with that first climate assessment where we basically presented our science in terms and in words that are understood by the public. Social scientists, philosophers, and all that, they have to offer a lot, but they have to make that step out of their comfort zone.
I'm afraid we have to move on.
Thank you.
Thanks, Thomas. Now we move beyond the Earth, and Athena Koustenis from the Paris Observatory is going to talk about atmospheres of planetary bodies other than the Earth.
Many thanks, John. I just wanted to start by saying that it has been a wonderful experience for me being part of the IAMAS family. They took me on board and took a huge challenge because not only am I a woman, but also I'm a planetary scientist and an astronomer. And I guess part of my talk today will be trying to convince you that astronomers do not sit and wait for their star to come by. Sorry. We do go to space these days, and we have actually very important things to do, and we're so connected to the Earth, as I'm going to show in a minute. This is about history, obviously, but it's also about very long timescales in the case of the solar system exploration, because we go back 4.5 billion years. So I can only wish IAMAS all the best for the next 4.5 billion years that are coming up, because we are halfway through the life of our sun. So I don't see anything on the screen. Let me try the usual trick. You close your computer, you open it up again, and it doesn't work. Okay. Okay. Well, I'll start talking anyway. I just wanted to say with respect to the previous talk that the space physicists are also very much concerned. There we go. Thank you. Are also very much concerned with climate changes, as I'll show you also in a minute. And I'm the immediate past president of IAMAS, but I'm also currently the president of the European Space Sciences Committee. And this is a committee that supported very much the COP21 in 2015 with a statement about the climate change on Earth. So we're very much involved in that. And my other concern right now is being on the COSPAR panel for planetary protection. And this is also very important. We're trying to protect the solar system, but also our own planet. So like I said before, in our environment, we have the sun as a star, and the sun is halfway through its lifetime. And we have 8 planets left because poor Pluto was demoted to be a dwarf planet recently. Not so recently, though, but still was demoted. But the 8 planets that remain, as you can see, are very different. And actually, we split them in 2 categories. The terrestrial planets on the one hand, the ones closer to the sun, and the giant planets that you find a little bit further away in the solar system. Among those terrestrial and giant planets, we have a lot of differences. On this chart here, I'm showing the Earth. Everything is calibrated to the Earth at 1. And you can see the semi-major axis, the distance to the sun, the mass, and so on and so forth. You can see the terrestrial planets, the ones closer to the sun, have small radii, masses that are about 20 or 300 times smaller than the giant planets, but they have higher densities by factors of 2 to 10, and they're fast rotators. And you also have a scale here on the right side that shows you the temperatures that go from very, very high temperatures, 700 degrees for Venus, which is the hottest planet in the solar system, all the way to Pluto, where you have minus 200, minus 300 degrees. So we have a large variety of different kinds of temperatures in the solar system and different kinds of atmospheres also. Here are some of the properties of the atmospheres of the planets in the solar system. Mercury doesn't really have an atmosphere, but Venus has an atmosphere, and Mars, and you can see both of them are composed of CO2, carbon dioxide. And I want to thank all the previous speakers because they've done some wonderful introductions to what my talk is going to be about with the greenhouse gases and the habitability conditions. You can see the Earth is sitting between the two, and it's the only planet that has a nitrogen atmosphere to talk of, unless you go all the way out to Pluto. Pluto is the only other planet that has a nitrogen essential atmosphere, 90% as the Earth. I'll show you that there are also indications around some moons of very dense atmospheres. But we don't know why this is the case. And Pluto has an atmosphere that collapses every 238 years. So it's important to understand how our solar system is evolving. And this comes through the study of the atmospheres very much. You can see all the giant planets, on the other hand, have atmospheres mainly composed of hydrogen and a little bit of helium. As I said, there are also moons with atmospheres in the solar system. A total of more than 160 moons exist in the solar system. Several of them have very tenuous atmospheres, like the satellites around Jupiter that you see here, Europa, Ganymede, Callisto, and Io. Some other moons have more consistent atmospheres, more dense atmospheres, and Titan is a unique body around Saturn that has an atmosphere even denser than that of the Earth's. So it's very important to look at all kinds of different atmospheres in the solar system. One thread I tend to follow is the habitable conditions. And you all know the habitable conditions. What do we need to survive? This is liquid water. Obviously, you've heard about it before. We need essential elements. That's for us astronomers, the SNOPs, the most abundant molecules on Earth. we need a stable environment, and we need energy sources. So far, the habitable zone that you can see here depicted for our solar system in the middle, has the Earth in the middle there, is residing at 1 astronomical unit where the Earth can be found, and this is where liquid water exists on a surface. But now, if you look a little bit further out in the solar system, you find that you have liquid water zones, actually, huge areas underneath the surfaces of some bodies, and these are the icy moons around gas giants. But before we go there, I want to start with the conventional habitable zone. That's the terrestrial planets, Mercury, Venus, Earth, and Mars. We talked about the Earth. You know the Earth better than I do, although I know that the Earth is a planet, so that's already a good starting point. But Venus and Mars are sitting on both sides of the habitable zone. What happened to them is a question. The atmosphere of Venus is very dense, very thick, as you can see here, almost 100 bars, and Mars is only 0.64 bars at the surface, and the composition is similar, but with such differences in the atmosphere, the bodies are unique on their own. So Venus is our closest neighbor. Its mass is almost that of the Earth's. The surface temperature, 730 K, very hostile conditions, very high pressure and temperature, an opaque cloud deck of sulfuric acid. It has been explored for quite some time, both from the US missions and from USSR. Very recently, I want to stop for Venus Express exploration. That's an ESA orbiter, and also give you an idea of the Akatsuki Japanese mission and what they did. When Venus was first observed by the Galileo spacecraft here, you can see the UV camera showing, probing the top of the cloud deck on Venus, and you can see how different it is as you go deeper below the clouds with the infrared range of the NIMS instrument. So Venus shows very different images depending on where you are, what kind of frequencies you're probing. I can't resist showing you some of the images of the surface of Venus here with the Magellan mission in 1992. And the Venus Express mission was designed to go and look at Venus properties all through the atmosphere. It arrived in 2006. It operated for 8 years, and it gave us some beautiful images like the ones that you're seeing here. On the left, again, it's the UV images taken in 2006. Again, the higher cloud deck on Venus. And on the right, you see the evidence for a polar vortex at the South Polar region. That image was taken in 2011. And it's similar, actually, to a vortex that was seen at the other pole, at the northern polar region, with Pioneer Venus many years before. And here we're probing in the infrared. So whether you're looking at the day side, for instance, of Venus, where you're looking at the solar radiation in blue on the left here of the different images taken in April 2006, or whether you're looking at the thermal radiation on the night side, that's the right side here, you see very different properties of the cloud decks, the very thick cloud decks on Venus. And from this we can infer information on such things as the winds and the composition. One thing that came out of the Venus Express mission, for instance, was the evidence of O2 air glow originating from CO2 photodissociation on the day side and coming then to the night side. This is an observation from Vertis. And the Akatsuki, beautiful mission, which managed to finally dock around Venus in 2015 and make numerous measurements of the aerosols, of the lightning, of the atmosphere and the surface in general of Venus, showed us, for instance, the gravity wave, a huge bow-shaped gravity wave in the upper atmosphere of Venus. This gravity wave that you can see in the upper image is 10,000 kilometers long, and it's suggested to be produced in connection because it's lying above some mountainous areas on the surface of Venus and at the sulfurous cloud top. Beautiful images. I wanted to just point, one of the first times I'm going to be discussing about the greenhouse effect greenhouse effect affects also planetary atmospheres. And on Venus, we have this very dense toxic atmosphere, very hot atmosphere that I have been discussing. And this is theorized and actually demonstrated by models to be the consequence of a runaway greenhouse effect on Venus caused by the greenhouse gases that we have in that atmosphere, which is currently composed of 96% of carbon dioxide, the remaining being mostly nitrogen. And this is a sobering statement or sobering warning about what could happen also on our own planet if we do not manage to actually find a way of stopping this increase of CO2 gases as on Earth, because on Earth we have managed at some point to stock and put all the CO2, for instance, in the rocks and the water in the ocean. This did not happen on Venus, and the consequences today is obvious. We should be extremely concerned about the processes such as burning of fossil fuels in large volumes and so on that could trigger such a runaway greenhouse effect on Venus, which boiled any oceans that could have been created in the beginning and allowed for H2 and O2 escape in space and result in the atmosphere we see today. So now I'm going to move to Mars. Mars is a planet that has a very tenuous atmosphere, very small atmosphere. The pressure on the surface is just 6 millibars. But it has always been a point of interest for humans to look to see if extant or extinct life could exist there. There has been an exploration going on for quite some time. You see all the different missions that we have today. I'll show them to you in a minute. In detail, but the Mars Express mission is a mission that is still ongoing around Mars. And the reason I'm insisting on this is because there have been such important results and such important findings from this mission on the detection of methane in the atmosphere, on the volcanism, on the auroras, and the rate of atmospheric escape. And even though the exploration of Mars was stopped for many years after the Viking missions, for instance, failed to discover life, it has started again now. And one of the images that the Mars Express mission has shown is this evidence of flooding of the surface on Mars. And this is seen by the Mars Express images, and it's a camera, and it shows that the collected data show that the Casey valleys, for instance, shown here, were generated by a series of megafloods and not by a continuous water flow on the surface. So we have megafloods on Mars, and again a greenhouse effect, very big one, that caused Mars to lose its atmosphere to space, because at some early time in the history of Mars, we saw that the planet's means of replenishing the atmosphere, it didn't happen. It turned into a desert, and geological observations suggest that rivers and seas disappeared. There's no liquid water really detected on Mars today, and we think that the cause for this, from recent results from the MAVEN mission, is actually the fact that the atmosphere of Mars interacted with the solar wind. A strong stream of electric particles arriving at full speed caught the particles in the atmosphere and dragged them out. It's something that looks like a cometary tail. So the Earth-like planets, 3 of them at least, sitting very close together, started very similarly, but had very different destinies. And the reason here is the different phases of water I have mentioned, and the fact that there are indeed ways with greenhouse effect to show that the atmosphere can disappear and the liquid water can disappear. We actually currently have 8 spacecraft, 8 missions on and around Mars, 2 rovers on Mars. And the ESA has put a link on their website that I'm showing here about the 10 things you did not know about Mars, but I'm sure you're dying to know about. This is number 1. If you want to see the 9 others, you can go on this website. But one of the things is that we have a whole program now that is going to go to return to Mars with an orbiter, that's the TGO. It's currently around Mars, as you can see on this slide, but also bring back some of the samples that we need to get back from the red planet. I don't hear the sound, but maybe it's here. It's more dramatic with the sound. But Mars Express has been exploring the red planet for quite some time. ESA has currently the TGO, the orbiter around, analyzing data. And there is a rover coming up next year. It's going to land on Mars. We'll drill for signs of life buried at up to 2 meters beneath the surface, and capture samples, put them on an orbiter that will encounter then a spaceship that will bring those samples back to Earth. This is the current program of Mars sample return to Earth, and it's a very important program that actually also takes into account the planetary protection policy. It's very important to understand that if we're bringing back samples from Mars, we have to be very careful about the scientific investigations we're going to do with them for possible contamination of our own planet. And also, if we go to Mars, we don't want to bring Earth life there and then claim that we have found life. We need to protect the environments we're going to, including in the outer solar system, where we have the giant planets that were explored by the Voyager missions quite some time ago. But in recent times, we have found a lot more about the two classes of giants. You know, gas giants are Jupiter and Saturn, with huge masses, mainly made of the protosolar gas, hydrogen and helium. Same composition, but less massive, are Uranus and Neptune. These are the ice giants. And so we have 4 different worlds in the outer solar system with Jupiter, Saturn, Uranus, and Neptune. Even though they have similar compositions, they have very different properties as concerns the internal source. For instance, Uranus does not have a very strong internal source, and this is why it has such a bland appearance most of the time. They also have different magnetospheres and circulation patterns. What we can see is that if we look at their temperature profiles and their cloud structure, we have methane, ammonia, all kinds of different clouds in the atmospheres of the giant planets. And they exhibit also an increase in pressure and temperature as you go lower in the troposphere. In the case of Saturn, for instance, here, the clouds are located much lower, and this is why we have harder time in seeing them. But we still can observe, and we can also explore. We have had a lot of years of exploration. Recently, the Juno mission is around Jupiter. You see the beautiful images of the Jupiter atmosphere here. The southern storms are indicated here. This is a mission that went into orbit around Jupiter in 2016. It's going to go on. It's been extended after the first 3 years. And it's looking at the planet to look at the formation mechanisms and study the internal structure. So around Jupiter, we have 3 moons that could present habitable conditions, and that's Ganymede, the largest satellite in the solar system, Callisto, and Europa. Europa has shown many indications of possible tectonic activity, and they have also, all 3 of them have hydrospheres, that is, undersurface liquid water oceans on a global scale. These moons are going to be explored by the Jupiter Icy Moons Explorer mission of ESA, flying in 2022, and they're going to be there's going to be an orbiter around Ganymede, and we're going to know how deep are those under surface liquid oceans, and what are the habitable conditions for these moons. We're looking very much forward to that mission. At the same time, we're looking at Saturn. Saturn has been a wonderful exploration target for the Cassini-Huygens mission, which was put together by NASA and ESA. quite some time ago. It flew by several of the objects in the solar system before getting very close to Saturn and looking at the storms that this planet can afford due to the meteorology there. Very complex meteorology. In Saturn's troposphere, you can see all of these features, but one of the most exciting features is the Saturn's hexagon that you can see up here, which we had a very hard time explaining outside a laboratory or inside a laboratory. It's a cloud pattern at the north pole of Saturn, about 78 degrees north, and the sides of this hexagon are about 14,000 kilometers long. The eye in the middle of this storm here is 2,000 kilometers wide. This is something that we'll never see on the Earth. I just wanted to mention that the Cassini-Huygens mission was a wonderful experience. And is it possible to have the sound? We had sound before for some of these images. It's more dramatic with sound. If we can't have the sound, I don't know why I have this thing plugged here. Anyway, this is the Cassini-Huygens mission that took off in 1997. You can see here the spacecraft in the United States. We had a wonderful launch in October 1997. You can see here at Cape Canaveral. We flew through some clouds of the Earth just for the dramatic effect. Yeah, I don't know why the sound is not playing. Anyway, thank you very much. So this mission, see, it's better with the music. Follow the red line. You see we're doing several flybys within the internal solar system, and then we go out to Saturn, which is the final target. But now you are inside the spacecraft. So hold on. You're inside the spacecraft. You're doing several flybys. You're flying by the Earth. You're flying by Venus. Right up, coming here. You're gaining momentum to get you through the asteroid belt. And then you're going to fly by Jupiter in 2000. And all of that time, radio telescopes on the ground are monitoring the mission, which arrives in the Saturn area in 2004 and stands there looking at the rings for some time. And then the spacecraft plunged actually through the rings and gave us some beautiful images revealing not only the planet that I just showed you a minute ago, but also two of its satellites. Cassini revealed Titan and Enceladus. Enceladus is a small moon, 500 kilometers in diameter, but it has geysers coming out of the South Polar region. And those geysers are laden with water vapor, methane, carbon monoxide, complex and simpler organic compounds. So you have a body here that has obviously an undersurface liquid water ocean, energy sources, organics in its atmosphere, and obviously is a good place for consideration for a habitat. The other place we looked at was Titan with this very dense atmosphere I mentioned also previously. We have had a ball looking at Titan. It's a very complex body. As this diagram shows here, it has a thick and extended atmosphere, mainly composed 95% of nitrogen as on Earth. We have methane in the atmosphere, organic compounds, which are hydrocarbons, nitriles, and oxygen species. And so you have oceans on the ground, you have lakes in the northern polar region, dunes on the surface, mountain regions, and volcanoes. So we also have the energy sources. And the temperature profile shows this greenhouse effect, increasing the temperature at the surface to a balmy minus 180 degrees Celsius. So what's important on Titan is, yes, we have habitable conditions, but we also have weather. And as Mark Twain used to say, climate is what you expect, weather is what you get. And weather is more difficult to pin down, but here is, for instance, the weather on Titan, for instance, a few years back. with some of the clouds coming up over the North Polar region. You can see them, the trails of the clouds here and here and here. And then you also have cloud systems here at the near the equator and all around the equator. And these clouds appear and disappear in long periods of time. You also have seasons on Titan, and a season on Titan is 7.5 years. So you get 7.5 years of summer, 7.5 years of winter, and so on and so forth. And with Cassini, we only explored 2 seasons on Titan, 13 years. The other amazing thing about Titan is one day is 16 days long, 16 Earth days long. So for those of you who say, oh, I only have 24 hours, I can't do everything there, you would have 16 days, and you could sleep for 8 days, actually. That appeals to me very much. So it's very important to look at these different places in the solar system because they teach us a lot about what could also happen to our own planet. For instance, what the weather is like on Titan today could teach us also about what the weather is going to be like on Earth in about 1 giga-year. Because actually on Titan we're observing this active hydrologic cycle. The methane plays the role of water. It's subjected to seasonal, longer-term changes as on Earth. And when we look at this, Titan appears to be an analog. It's different materials, but it's still something very similar to the Earth. And when we have the evolution of the solar luminosity with time, where it's going to get hotter out there, it makes it almost unavoidable that in about 1 giga-year from now, the tropopause temperature of the Earth will be elevated to the point that loss of the Earth's ocean by evaporation and then stratospheric photolysis of the water vapor, this will occur. And then you will end up having the same thing as a Titan where all the liquid is going to be confined at the poles. So in the future, we're going to explore Titan with several missions. I proposed a balloon in my own time, but the mission Dragonfly is going now to go to Titan. It's going to be launched in 2026, and we'll learn much more about this. I'm going to end by showing you just a couple of pictures of the ice giants, Uranus that we talked about before, that has these beautiful images taken by the Keck with the clouds brightening up in June 2017 between 26th of June and 2 of July. And the clouds here on Neptune, beautiful clouds that you can see in very much of detail, composed of methanized crystals. So leave you with food for thought. We know that terrestrial planet climate studies can give us insights on the climate changes that are currently affecting the Earth. These changes in climate and the potential habitability, as was mentioned before, we can see on other planets, the terrestrial planets and Titan. We can share the lessons learned between planetary science and Earth science. And we see that we have deficiencies in our understanding of what could make an important difference in climate forecast for the near future of the Earth. And the study of our planetary environments, I think, is very important because we also have exoplanets now that we know of. The atmospheres there also need to be explored. We're doing this with big telescopes. And I want to end by congratulating IAMAS, and as I said before, wishing you a wonderful next 4.5 billion years. Thank you.
Well, that was a fascinating perspective on atmospheric science. Time for one question. Anyone?
Oh, I forgot to say. If you want to know more about everything I showed in such a brief expose right here, tomorrow we have the Union Symposium number 6, which is on recent planetary discoveries. And so please come. It's at 1 o'clock, 1:30 o'clock, and through the afternoon we'll tell you everything about planetary science.
Great. Okay. Thanks very much.
Thank you.
So our last talk is from Andy Brown of the European Centre for Medium Range Weather Forecasting, where he's the Director of Research. And he's going to talk on weather prediction, progress, and prospects.
Where's it up there? Okay, and thank you very much for the invite. A pleasure to be here. I feel a bit coming back down to earth now. So I'm going to show quite a lot of examples from ECMWF here, but hopefully be managing to use them to show some sort of general points and directions in the sort of weather community. I thought to start just with a reminder of sort of why we do this stuff. I mean, this is some statistics from WMO over a 30 or 40 year period, where they identified approaching 2 million deaths and $2.5 trillion of economic costs. So, weather really matters. We can't prevent bad things happening when there's bad weather, but better forecasts let people take action, whether it's evacuating people, getting resources in place, economic decisions. So, there's huge societal value in better weather forecasts. And I hope I can convince you that really what we have achieved, and this goes right from the academic community into the operational community, we've come a huge way in managing to make the impact of severe weather much less than it was, but there's a need and potential to go much further. And this is just one example, Hurricane Irma on the left, looking at a sort of 10-day ensemble forecast, the different colours, the different days, and you can see how for the first 5-6 days there was really high confidence in the route through the Caribbean. By the time you got out to today, sort of 6 to 8, if you're trying to decide which side of Florida you wanted to evacuate, there's probably not enough information there yet. And just looking at what these models look like, that's meant to animate, but no, it did slowly. So this was the day I was producing this talk, 10 days or so ago, just looking at the ECMWF forecast. This is just a simulated satellite image out of the forecast model. And just what you really just notice just how like weather it looks. This is all in a computer, just using our knowledge of the atmosphere, equations, parameterizations. You can see the storm systems in the Southern Ocean, tropical disturbances. So, but based just on our understanding of atmospheric science and encapsulating into a computer, you really can produce something that looks like weather. And this is just a single snapshot going to visible rather than infrared now. And one of those is the Meteosat geostationary picture, and the other one's the model. And you really have to look quite hard to work out which is which. If you look hard enough, it is slightly blobbier. The one on the right will be the model. But these simulations, from where we were, we heard about some of the history of the early ideas to where we've come to. I probably don't really need to talk about the history because we had it explained so well earlier on. Just picking up on the Willem Bjerknes, I'd say that's separation into getting an initial condition and then following by the prognosis. That really is the heart of how we're doing weather forecasting today. Probably just mention actually Lewis Fry Richardson as one other key person in the history. I think the first person that really conceived of numerical weather prediction. He was actually conceiving a big concert hall with an army of people in it, all passing information to the people next to them. But I think that was, in a sense, the start of thinking of a sort of low-resolution numerical model. And if you go to the computing, again, we've heard about von Neumann and Charney, some of the earliest numerical weather prediction back in the 1950s, ENIAC, so a one-layer model, 400-kilometer resolution over North America, which took 24 hours. In 2006, you could do that in 1 second on a mobile phone. I don't know how long it takes now, but it's huge developments in what you couldn't have even conceived back in those days of where we'd be now. So I'm sure this is very familiar to most of you, just how we do NWP, and I'm focusing on the global side here. So there's a huge international exchange of observations, whether that's satellites, commercial aircraft are all continuously measuring as they fly, radiosondes, radars, shipping, buoys, Argo floats in the ocean. So huge amount of data and a huge free international data exchange of that data. I think there's a lot of foresight shown in realizing that no country can forecast the weather without reliance on others. So huge exchange of data. a data assimilation process to bring that into a model, and then different numerical schemes, but essentially splitting the globe into grid points or spectral intervals. And so in the ECMWF system, we're now at a 9-kilometre global resolution and 137 levels. So millions and millions of grid points, millions and millions of individual bits of observational data coming in every day. And yeah, you can imagine the computational requirements are staggering. I'm not going to labour this plot because we showed it earlier, but maybe just something that I think we've failed to just shout about as a community enough of just how far we've come. You know, the fact that a 6-day weather forecast now is as good as a 3-day weather forecast was 30 years ago. And if you think about it, it's one thing to be told there's bad weather coming but not have enough time to do anything about it. It's another thing to actually have that extra time to be able to react to it. So I think it really is something that, as a community, we've actually failed to champion as much as we should have done. Just actually what a success story this is, which doesn't mean there's not further to go. This is really a zoom and the more recent part of that time series. So again, this is looking at 500 hectopascal height. It's looking a different way around. It's saying how many days we can maintain a certain level of forecast quality. I think this is 85% anomaly correlation. And the different coloured lines are the results from different operational centres. And so the point you meant to see is that they're all going diagonally upwards. So somewhere between 4.5 and 5 days lead time to that given level of accuracy we could manage in 2002. And we're up at somewhere between 5 3/4 and 6.5 days now. So different modelling centres around the world are all getting better. But really what I wanted to talk about was what's making us better. And one way we can try and learn something about that is if you look at the dotted line on that's rather more horizontal than the other lines, that's the new reanalysis that we've just done at ECMWF, the ERA 5 reanalysis and forecast from that. So that's taking a modern forecasting system and using that same fixed forecasting system to reforecast all the years in the past. So the main operational lines have the advantage of bigger computers, new observations, and new science coming in over that period. Whereas that dotted line has fixed computer, fixed model, and the only thing that's changing is the observations coming into it. So the fact that that dotted line is going upwards, crudely gives you a measure of, we have got newer and better satellites and other observational sources than we had. So those new observations have contributed to the improvement in weather forecasts. But it's not going up nearly as steeply as the full lines. So the bigger computers and the better science in these systems has also contributed. And you can't see it on this plot, but the bigger computers, it is a significant part of that. If we get a bigger computer, we can run with finer grid squares. That definitely helps and has contributed. But arguably, the single largest contributor to that rapid increase, it's the clever people. It's the better models. It's the better techniques for using satellite data. It's not just the satellites themselves. And I think at 100 years of IAMAS, it's quite a good time just to remind ourselves that while the infrastructure is crucially important, I spend lots of my time arguing for bigger computers or working with space agencies. That really matters, but it doesn't matter any more than having a community of experts working on this stuff. This is just a Met Office example, but really showing the same thing. This is just showing time series in the Met Office system of errors in the model. So now down is good, and the different vertical lines are where various upgrades to the modeling systems are introduced. And you'll see some of them where it says things like N144, N216. That's increasing the resolution of the models. That really is using a bigger computer. 3D VAR is a new data assimilation system, new way of using data. 8OVS is a new data. More resolution, more models. But again, this mix of different incremental improvements but a lot of them coming from the science as well as from the infrastructure. That was focusing very much on sort of 500 hectopascal height. I think it's fair to say 20 years ago, the height of our ambition in NWP was probably to broadly get the synoptic pattern right. You know, it would be good enough if we could say, is there a storm system likely to be coming, or a big high pressure? I think the level of ambition and user demand has changed now, so it's much more focusing on sort of local weather, risks of extremes. And so ensemble systems, looking at precipitation, looking at near surface temperature, and really trying to really directly forecast and predict, you know, the risk of what's really going to give the local impact that people are going to respond to. So that's where we are now. Where do we want to get to? I mean, this was something from the ECMWF strategy from a few years ago. I think we could broadly characterize the situation as most of the time we can forecast reasonably well for a week ahead. You know, there'll be times when we can do better, there'll be other times where this forecast busts, but by and large, we're reasonably accurate for a week. But you know, we'd really like to be able to push those warnings out into the second week, stretch further ahead. Going to a more continental scale, large-scale patterns. I remember in the UK a few years ago, there was a winter where there was just storm system after storm system causing more and more damage. And you know, what the government wanted to know was not so much what's the next single storm going to do, but you know, is this going to go on for 2 weeks or a month or for 2 months? So the sub-seasonal prediction, trying to get regime changes, and then out onto a longer scale, seasonal forecasting. Can we really push out to get, you know, actionable seasonal forecasts, particularly away from the tropics? So really just trying to come from where we are, but just push out the how far ahead can we give usable information. So I think we see the heart of this, and I think other centres are on a similar approach. So very much a seamless approach to modelling and analysing, and an Earth system approach. You know, it used to be very much atmosphere or atmosphere and land. I'll show some examples of where we're really pushing beyond that. We continue to see value in higher resolution and very much ensemble systems. You know, I think, again, it was raised, the idea, concept of chaos this morning. In a sense, I think, particularly if you're pushing further out, but even right from the start, the idea of trying to deterministically do this, you know, really using ensembles and really trying to look at them in a probabilistic sense. We're not doing ensembles just to get the mean, but just to take the ensemble mean. We're really trying to produce products which are directly giving probabilistic information. And I'll say something about scalability, so computational efficiency, and some of the challenges that are coming there. So this links nicely to another of the earlier talks, but the use of satellite data. So this is the number of different satellite data products that we're actively assimilating at ECMWF every day in the forecast. So in the 1990s, we were perhaps using 10. Now we're using over 70 different satellite products. And obviously the satellite data itself is obviously absolutely crucial and essential to that. But how we use it, as again was talked about earlier, there's a huge science in that. In the early days, in the sense we couldn't, even though the satellites were around in the 1980s, we couldn't show value of using satellites in NWP. Whereas now, if we look at the reanalysis, the satellites are clearly giving value. So we've learned how to use this data, and we've moved on from trying to offline get from satellite into a temperature or moisture profile and assimilating that into more directly working with the radiances. So we don't use many pre-processed satellite products. We're using the satellite data directly. And this was also touched on, the use of novel and new satellite information. So this is the Doppler LiDAR in space on the ESA Aeolus mission. Because one of the gaps in the global observing system is we don't have very much 3D information on wind. You know, where civil aviation is flying, we get lots of wind data on the main flight paths. We can get some information from cloud tracks to infer winds, but there's not very much direct observations of space. So this is really just a single example snapshot where using the Doppler LiDAR, and it's managing to, as it heads from the equator down over the South Pole and up north again, you see the blue and the red is the jets that it's correctly picking out. And we're just experimenting with assimilating this in our forecast system, and we can show some benefits of it. At the moment, very much a proof of concept, with a hope that this will become something that turns into sort of further operational satellite missions. Not going to say much about the details of the data assimilation, but just to stress it's absolutely crucial how we're doing it. The 4D-VAR data assimilation that we brought in over 20 years ago now, what we start with is a previous forecast shown in the blue line. Then we'll have various observations come in, shown in the green stars, and what we try and do is combine those together by minimizing a cost function to come up with a corrected forecast shown in the red line. And what that's doing is it's taking into account the fact that, of course, the previous forecast has errors in it, but the observations have errors in them as well. And it's trying to optimally bring together these different sources of information. Because if you like, the previous forecast is bringing forward knowledge of the previous sets of observations. And developments here and using ensemble information to even in assessing how much weight should we give to our previous forecast, if the ensemble system was very confident, would give the previous forecast more weight. If the ensemble system was very spread, we would know to relatively give the observations more weight compared to the model. So a huge science in the data assimilation. On the modeling side, as I said, early models were very much doing the atmosphere or the atmosphere and the land, and things like the sea surface would just be an externally imposed boundary condition. We, in common with a lot of other centres, are gradually moving to directly model more components of the Earth system. And that's partly because these are just useful things to forecast in their own right. We'd like to be able to forecast sea ice or ocean currents, but partly because of the feedbacks on the atmosphere. So just to give one example, on the ocean side, many people, for years, everybody's tended to use a coupled ocean, certainly if you're doing climate modelling or seasonal forecasting, and there have been talks this week where people are talking about, can we show benefits for sub-seasonal forecasting? About a year ago, we switched to actually, even from day zero, we're now, to forecast the weather, we're having a coupled ocean in the forecasting system. And this plot, I won't go into the details, but just showing in the tropics in particular, we can see that the temperature and humidity forecasts are improved even in the first week by having a coupled ocean including in the system. And if you look at tropical cyclone statistics, as you'd expect, when you have a coupled ocean, you lose an infinite heat source, so tropical cyclones tend to get less intense in the models. This is just looking at the PDF of errors in our forecasts. The blue is the uncoupled, and the red is the coupled. Now, as expected, the whole distribution moves to the right. The tropical cyclones aren't so deep. But the really striking fact is what it's done is not symmetrical. On the left-hand side of the plot, you've got where previously we had a lot of very serious over-predictions of intensity, and those have almost entirely gone away, where we've only slightly increased on the other side. And that's effectively because cases where there was a shallow oceanic mixed layer, if you're not using a coupled model, you can take far too much heat out of the ocean into the tropical cyclone, and that's alleviated. So we are finding that this inclusion of further Earth system processes does improve the quality of the forecasts. In terms of weather and climate, just wanted to show a few slides, just really emphasizing the commonality of the issues here. This is a very old plot now. I think this was from the Met Office system, but just looking at the evolution of sea surface temperature forecast errors. So blues are cold and reds are warm. Even in the one-day forecast, just on the equator, you can see a hint of blues. It's just going slightly cold, and you can just see that growing in time through the 30-day forecast error, or the bottom panel is the climate model error. So just as a way of understanding what's wrong with the climate model, looking at these shorter range forecasts, it's cheaper, it's easier to understand. You don't have to disentangle quite so many feedbacks. So a huge power in using weather models to improve climate. We're very interested in the sub-seasonal timescale, trying to do better week 2, week 3. There's been a session here at this conference, and this is just a plot from the sub-seasonal database. So there's a database available to the research community to look at the predictions from the leading global models. Lots of diagnostic work to be done. Delighted to see lots of talks and interest in this database, and that's trying to move to a next stage of the project where there'll be more coordinated experimentation to really try to dig into, why are some models not, how much predictability should we be able to get from land surface? How do the stratosphere-troposphere connections link? So I think, opportunities for the research community to get further involved there. And on the seasonal system, again, effectively our seasonal forecasting system is to all intents and purposes identical to the medium range forecast system. Performs very well in the tropics. As has been discussed here, there's still absolutely research challenges to get seasonal skill in the extratropics and to understand some of the teleconnections. So plenty still to do. Also just wanted to advertise, there's lots of really quite basic science where there's still things where we're not doing as well as we'd like to, and indeed we need to. This is looking at the ECMWF system, just looking at maximum minimum temperature errors across summer 2017. And you can see a fairly systematic over a large part of Central Europe. We tend to be slightly too warm overnight and slightly too cold by day. And that still feels like a fairly sort of simple and fundamental problem. So we've been working a lot using supersite data. So this is Lindenberg in the States, but obviously there's ARM in Lindenberg in Germany, there's the equivalent of ARM here, Cabau in the Netherlands. But really trying to use detailed process research to dig into what are the causes of these errors. And suggestions, which I won't go into in detail here, but that the land-atmosphere coupling is the wrong strength. So our soil is too responsive. But I think just it's always tempting to get into the really big, complicated things, but this is still some pretty fundamental, basic science where we still need more from the research community. I'll skip over those. So just the last couple of minutes, I just want to talk about some of the newer challenges and the computational challenges. I mean, I think it's fair to say that for the last 10 or 20 years, every 4 or 5 years, we and other centres would make a case to spend some more money. We'd buy a new supercomputer. That new supercomputer would be more powerful than the last one, and away we go. That's been ceasing to be true. The amount of computer you get for your pounds is not going up as fast as it used to, and the changing technologies mean that some of the codes that we've used for years, it's not clear that they're still going to serve us well in 5 or 10 years' time. So we've been doing a number of strands of work on this. I mean, I guess this is fairly incremental, but just looking at even the precision we run our models in. How many bits do you try and store all these results when you're doing the weather forecast? And we have great accuracy, but then you could argue about, in some of the parameterization schemes, we don't know whether to put in the number 3 or 5, so do we need to worry about the 15th decimal place? And this is just some work showing that if we take the ECMWF system and run it in single precision rather than double precision, we can get about 40% more throughput on the computer. Or more interestingly, we have 40% more computer left over that we can invest in a better representation of ozone or aerosols or data assimilation. And reassuringly, you can't tell the difference. So that's using the computer we've already got more efficiently. But what about future architectures? As you get to more sort of hybrid computers and GPUs, lots of the systems we use, effectively, nearly all global weather centres have been using similar techniques for 30 years or more. They've served us well. It's not clear that they will work in 10 or 20 years' time, or will work efficiently. So I'm not going to go into the detail of this, but we're working on a completely new dynamical core. And I think maybe what's different here is it's really designed around what do we think will run efficiently. The paradigm stops being scientists invent something, then give it to clever computer person. The actual design choices up front need to be affected by where the computers are going. And I think my last example of linked to computational science is just a new research area. Where is the potential of machine learning in all of this? Now, I may be just being too conservative and not visionary enough, but I don't believe you can do away with the model at the absolute heart of this. It's such a complex non-linear system. I don't believe you can do away with the whole of that. But there probably are lots of places or building blocks in our production chain where you can do more with artificial intelligence. All the data we bring in, we use a tiny fraction of it, we quality control it, we thin it, we do bias corrections. Can some of that be done further with new machine learning techniques? Some of the model components, could we replace the radiation scheme, for example, or the cloud scheme with a simple emulator that ran more efficiently? Or after these models run, we're producing, gazillions of bytes of data. How do you extract signals and information out of all of this? So I think there's opportunities and a need to sort of work with a whole different community to take advantage of that. And my final slide, so where's this going? I hope I've convinced you we've been getting lots better. I think we've been getting lots better, but we need to keep getting better. And to do that, we absolutely need various communities to work together. I noticed I failed to put weather and climate. I'm taking that as an absolute given. The issues faced by both communities on the modelling side overlap so strongly. We absolutely need collaboration between operational centres like ECMWF and the academic community as represented in IUGG and IAMAS. I hope I've given enough motivation where there's things we still don't understand. And I think a new axis where the sort of physical scientists and the computational scientists need to be even closer together than they've been before. And I think if we do all those things, those scores and accuracy will keep going up. And I think that really does make a difference to society. Thank you very much.
So, any questions for Andy? I can see here. Yeah. Thomas.
Yeah. I've got one, quick one. Don't you think you're being a bit pessimistic, Andy? The use of FGPAs and other computational structures do give plenty of opportunity to keep on your increased computational.
Oh, no, absolutely they do. I think the point is we need to do work to be able to use them. In some cases, it's changing the types of algorithms we use or changing the way they're coded, because I don't think what we can do is, these are 2 million lines of code. We can't every 4 years completely recode it. So some of these ideas are trying to abstract away the science code from some of the computational code. But yes, it's so we can take advantage of these new computers that we need to do the work. And if we can, yes, absolutely, they can contribute.
Thanks very much for your presentation. You pointed out the crucial role of satellite data.
Yep.
There are many countries who send up large numbers of satellites, such as China and India.
Yep.
Are these data available for the centers like ECMWF and other centers?
By and large, yes. Sometimes there's work to be done to get the data feeds flowing, but yes, we're working actively with some of the new Chinese satellite data, for example. The only other comment I'd make, actually, is yes, satellite data is hugely important, but so is some of the in situ stuff. These weather models are now clever enough that they're themselves deciding what biases to associate with the satellite data. And if you don't have some anchor for that from in situ measurements, there's a danger of it all running away into model world. Okay, thank you.
So I hope you enjoyed the talks. I think they were exactly what we'd hoped for when we planned this event some time ago. I think they were authoritative and wide-ranging from real-world experts in their field. So I hope you enjoyed them, and let's thank all our speakers from this morning.